In today's episode, we dive deeper into the world of quantum computing and meet the visionaries turning this groundbreaking dream into reality. Quantum computing holds the promise of solving incredibly complex problems at speeds far beyond what classical computers can achieve, thanks to its use of qubits, the core building blocks of a quantum computer. The challenge? Qubits are extremely sensitive to background noise, which leads to errors. But in an exciting breakthrough, MIT researchers have developed techniques using a superconducting qubit called Fluxonium to achieve a world record single qubit fidelity of 99.998%. That's the best in the world so far. Atlantic Quantum is now on a mission to commercialize and scale this game-changing technology. We sat down with Bharath Kannan, the co-founder and CEO of Atlantic Quantum, to learn more about his vision and how he plans to shape the future of quantum computing. Stay tuned. So Bharath, it's an absolute pleasure to meet you. I've seen, your company make headlines quite often of late. So we're certainly very excited to learn more about it. But first, tell us a little bit about yourself.
So I'm Bharath. I'm the CEO here at Atlantic Quantum, originally from New Jersey. Grew up there, did my undergrad at Rutgers University in physics. Basically spent my entire first 20 years there before moving up to MIT to study applied physics, electrical engineering, specifically in quantum hardware. I've always been kind of a physics/computer nerd. And for a good part of my, the start of my education, I've always treated these things as independent things. And when I first came across quantum physics, that was very exciting to me as a topic. And then during my undergraduate years at Rutgers, I learned of this field called quantum computing, right? Which has been, in literature and out there since the 80s. This is when Feynman first proposed this nominal notion of a quantum computer. So it's been out there, right? But really the hardware started getting pretty interesting late 2000s, early 2010s. This is when things started to pick up. In fact, I think Google started their mainline effort 2013 plus minus 2014, somewhere around there. And in fact, that was the headline that kind of caught my attention when I was in my first or second year at undergrad. I was working on solid state physics, similar to the transistors and semiconducting materials and whatnot. I was doing some research on similar topics there. But I also had this passion for computer science. And so once I found out that there's a way to kind of combine these two things, right, into what could be the next frontier of compute, this was very enticing for me. But in addition to that, what I then learned was a lot of the problems we deal with in physics, not just physics, chemistry, material science, right? They're very hard problems. And it turns out a lot of the times they're hard because we're unable to predict what is the solution, or at least even have a good guess before we have to physically do it, right? And so we spend a lot of time in the lab just trying things based on heuristics. And that can be pretty demoralizing at times, right? Because you don't feel like you really understand what's going on. You're trying to build up some intuition based on what you see and correlate that with maybe some very basic model of what you're trying to understand, but really doesn't include any of the complicated things that are in the system of actual interest. And that frustrated me, right? Because as a physicist, I want to understand how things work. And it was kind of, we have these beautiful, very powerful supercomputers, and even they're not able to help me understand what I'm doing before I do it. And so that's when I learned that for some of these problems, particularly, being able to run those computations on a quantum computer actually makes that tractable, right? The ability to know if what you're working on is even remotely in the right direction before actually committing the time and energy to do it. For example, in batteries, industrial chemistry, pharmaceuticals, right? All of these industries could benefit from being able to predict with some level of confidence that the molecule you're working on is at least in the right vicinity of the correct solution, whatever that problem may be. So this is what really got me excited, is that ability to, I kind of see this as a means to an end. I want to go back to doing physics, but I can't do physics because I don't have the computer to do it, right? So let me build the computer first.
For your physics projects down the road, yeah.
Maybe in a few decades I can go back to that, but for now we got to make that.
Well, as I was saying, Atlantic Quantum is gaining some traction of late. So tell us more, like why should the world care about Atlantic Quantum and its mission?
Yeah, I mean, first of all, again, taking a step back, why quantum? Right? As I mentioned, there are a lot of very interesting applications, even beyond just for scientists, right? Very broad impact. If we're able to predict whether a certain drug molecule binds to, like the protein binds to a receptor in a certain way with even some nominally higher fidelity, right, than we can today. Or if we can reduce the energy consumption of a certain industrial chemical process by developing a catalyst for it, right? These are very exciting things. You're not necessarily focusing on one problem, right? You're kind of taking a step back and addressing many problems simultaneously. At the end of the day, it's a computer, right? In the same way that classical computers have changed our lives in ways that we notice every day, like your smartphone, but also in probably the vast majority of uses of computers that are behind the scenes, right? Quantum has the ability to have that broad defining impact, right? And so that's why it's super exciting to be able to work on that. It is, I believe, that next gen of compute, right? Now, there are certain implications with quantum that are less than rosy. For example, the implications that come with secure comms and the ability to factor large prime numbers and therefore break RSA encryption. With all new technologies, there are good things that you can do with it, and then there are scary things that can happen. Regardless of that, these are things that can and likely will happen. And so to me, that makes combination of those types of things is what makes me think that quantum is inevitable. We will build a quantum computer, and by we, I mean the community as a whole. I want to be a part of that, right? I mean, ideally, I'd like to be the one that builds it, the actual one that gets all the way, or one of the ones that get all the way. And so, to me, this is an opportunity to mark my kind of place my foot in the history books.
You're past to pulling it off, but once it does happen, I'm sure it will be very gratifying. And when I asked ChatGPT, the word Fluxonium qubits came up a lot with regards to your company. So tell us a little bit about that and why that's unique.
Yeah. So starting from a high level, there's this notion of a quantum bit, or a qubit, as we call it, right? This is much like the bit is the fundamental piece of information in a classical computer. A qubit is fundamental piece of info in a quantum computer. Now, much like there are many physical ways of realizing a classical bit, right? Ultimately, a classical bit is 0, 1. It's just a switch, right? On, off. That could be a vacuum tube like we used to have. It could be a literal mechanical switch. Or it could be the transistors that we use today, which are electrical switches, right? Solid state. Much like that, there are many physical ways of realizing a quantum computer. What we're working on is a type of qubit called a superconducting qubit. So the way to think about a superconducting qubit is that much like you have semiconductors, which form the basis of your transistor and classical compute, a superconductor is a different type of material. A semiconductor is a semiconductor, right? So it sort of conducts, depending on what you do. A superconductor is a conductor without any electrical loss at its kind of simplest level. Hence the term superconductor, right? So it conducts perfectly. Now, you can, it turns out, build electrical circuits based off of superconductors that are effectively akin to artificial atoms. You can actually use circuits to create your own energy levels and engineer them based on how much capacitance or inductance you put into the circuit. So we're able to engineer artificial atoms, which we then use as qubits. Now, within that family, much like you have, protons, neutrons, and electrons that form the periodic table of real atoms, we have capacitors, inductors, and this element called the Josephson junction, which is just another type of electrical element with superconductors. You can take those three and form a periodic table of artificial atoms. And within that periodic table, there is the so-called Transmon qubit. This is what Google, IBM, Rigetti, basically almost everyone. It's the simplest superconducting circuit you can make to act as a qubit. And that simplicity is nice. It definitely helps in the small scale because you're able to put these things together pretty easily, and you're able to test these things out very quickly. But it comes with certain drawbacks. One of them is the Transmon's susceptibility to noise. So this is one of the biggest issues with quantum computers today. What do we mean when I say noise? Well, if I encode some information in my qubit, say I put it in 1, if this was a transistor, it would stay as 1 probably forever, right? You could do 2 + 2 on your phone for the rest of your life, and it will never say anything but 4, right? For a qubit, unfortunately, regardless of your modality, often that information is very easily lost. As you can think of it as like, there's some noise in the environment that's kind of kicking at your qubit. So if it's in a 1, maybe it flips to a 0, right? And now that's it. Your information's gone. So the Transmon has some intrinsic susceptibility to that noise, partially due to the simplicity of the circuit, right? It's a trade-off. Now, the Fluxonium that you mentioned is a different type of artificial atom where we've rearranged the circuitry. We've added, to be specific, an extra inductor to the circuit. And this is now a slightly more complicated circuit, right? So you kind of lose on that axis a little bit. But with that, I like to say marginally added complexity, you get a lot of interesting benefits. The first one being, one way to make your qubits better is to kill the noise, right? Just make it so that there's no noise. So when we say something is high fidelity, that means, there's no low noise on the operation, right? So we say a high fidelity operation, it means it works most of the time, right? And the higher fidelity means the more often it works, right? So one way is to make your materials better, right? That's like getting rid of the noise. This is something that we should all do. It's difficult. It's hard work, right? But it's important, but it's slow. An alternative is, hey, the noise is there, okay? It's going to get better, but it's there, and
it's inevitable.
It's inevitable. We'll get better at dealing with it, but like it's always going to be there to some degree, right? What happens if I just put headphones on my computer, right? It doesn't hear the noise. Noise is there, it doesn't hear it, right? That is what this extra circuitry in the Fluxonium essentially does.
Nice.
It kind of puts headphones on the qubit such that the qubit can operate without being perturbed and disturbed for longer periods of time. Now, this is good, but you then have to take that property and translate it into actual improved operational fidelity. What does that mean? I told you, for example, I have my qubit, I put it into 1 state, right? And I want to flip it. I want to go from 1 to 0. Right? So I want to do a not operation. Now, if I have this noise with the Transmon, typical fidelities, we measure them in terms of a percentage, right? So how often does it work? Typical fidelities for the Transmon, 99% to 99.9%. So basically once every 100 to 1,000 operations, you get something that wasn't what you intended, right? This is good, but clearly not good enough if you're trying to run a real algorithm, which is obviously going to have trillions and trillions of operations. And there are other ways to also deal with this, which we can talk about in a minute. But we want to make that physical performance better, right? And okay, you say if the qubit doesn't hear the noise as much, that's good. That probably means that the fidelity gets better. And if that is true, you have to take some care to translate that. We call it coherence, the coherence time of the qubit. You may have heard of this. Transmon is typically around 100 microseconds for state of the art. With Fluxonium, we're about 10x better. We can do about, in the millisecond regime. That's not enough on its own. You have to then make sure you take advantage of that higher coherence to translate it into the operations. That's what we did. That was the last thing we did at MIT. So in Will Oliver's lab, which is the lab that, Will, myself, and several others founded Atlantic Quantum, and we spun out of. One of the last things we did at that lab was showing that not only do you get kind of a qubit that has higher coherence, right, but we've translated that into very, very good fidelities, about a factor of 10 improved on what others have. So that is one thing. Now, that in and of itself is not sufficient. A better qubit is good, but it's not really going to change the game in some sense, right? What we need is, in addition to better performance, is scale, right? If we're in the regime of tens of qubits, a few systems out there with 100 or so qubits, this is far cry from where we need to be to run the applications that I mentioned earlier, whether that's drug discovery or running Shor's algorithm for cracking encryption. These are going to require, optimistically, hundreds of thousands, realistically, millions of qubits. Now, getting from 100 to 1 million is a big chasm there, right? And the way we do things today, an additional disadvantage of that, that comes from the simplicity of the Transmon, is the type of controls you need, the pulses you have to generate to apply the operation, say to do a NOT gate, right? What do I need to do to the circuit? What pulse do I need to apply to it? Very sophisticated, complicated pulses that require very sophisticated classical electronics to generate. And the way to think about it is you have essentially a classical microprocessor for every qubit. So 1 qubit, 1 classical computer. 10 qubit, 10 classical computer. If I'm going to have 1 million qubits, am I going to have 1 million classical computers for 1 quantum computer, right? Just to generate these pulses. It doesn't make sense. So we asked the question, in addition to making a better qubit, right? Can we take advantage of that qubit for simplifying the control, okay? Such that we're actually able to integrate the control and manipulation of the qubit alongside the processor itself within the same package inside of the cryogenic volume. So that now you have a fully integrated circuit that you can lithographically scale and get some kind of a Moore's law equivalent to get kickstarted, right? That doesn't exist today. Every qubit you add nowadays is that much more work and that much harder, right?
Yeah.
It's very painful. So these are the problems that we want to solve, right? We want to make the qubits themselves much, much better. Simultaneously, make it easier to scale to thousands, tens of thousands, hundreds of thousands, and hopefully eventually millions of qubits.
It's like a platform technology.
Yeah, I mean, we are building the processor itself, right? And it's early days. There's no standardization in this field, right? Everyone's kind of doing their own thing. You come and talk to me, and I give you this great pitch, and you go and talk to someone else, they'll give you another great pitch, right? So there's a lot of great ideas out there. Everyone's trying their own little twist on this. We'll see what comes out in the end.
Well, I mean, that kind of dual functionalities definitely sounds great. But how far have you come, and what's your next milestone? Yeah,
so as I mentioned, we were a spin out from Will Oliver's lab at MIT. We started the company a little over 2 years ago, raised our seed round with the goal of essentially showing that the Fluxonium qubit is not just a qubit with better coherence, but whose properties translate to higher fidelity by a factor of 10%, right? We've done that. So that was the key milestone for our seed. And now, as I mentioned earlier, we want to show that our qubits are compatible with this notion of an integrated circuit, right? Without sacrificing performance. So if anything, continue to make the performance even better, right? Add another factor of 10 on our gate fidelities. And at the same time, show that we can do that operation in a fully integrated way where the control signals are generated co-local to the processor itself inside of a cryogenic volume, as opposed to, you probably saw at the MIT lab, all these cables, right, that need to go from near absolute zero to ambient conditions, and you have to maintain the signal integrity over that huge temperature gradient. It kind of looks like the vacuum tube computer. I mean, much more beautiful, right? They're gold and shiny, and sometimes we get lost in that beauty. But from this perspective of scale, it's not so beautiful, right? Scaling that type of approach seems difficult.
What's the future? I mean, do you have some kind of a timeline?
Yeah. So, our North Star is to really build the first utility scale quantum processors. And what do I mean by utility scale? I mean, things that running algorithms that people actually care about, not some contrived problem. Something that actually gives value. We think that we will be able to have processors of that quality and size in the early 2030s. This is really our North Star. Now, that's a 10-year journey, right? There's a lot to do between now and then, but that notion, right, of for example, you probably heard of the Google quantum supremacy experiment, right, where they ran essentially what is a random number generator. The first algorithm per se that did something faster than what a regular computer could do. It's interesting and it's important to show that that's even possible, but it's not really useful, right? And we're a long way between some demonstration like that and an actual useful quantum computer. And the only way we're going to get there is if we can scale quickly, right? And get some sort of a Moore's law applied to quantum, right? And we can't do that without a technology that is scalable, right? And in our opinion, that is, you need a high performant integrated circuit to do that.
Fascinating. And, I have to say, there are many, I guess, early kind of entrance players out there as well, right? That are really focusing on the large scale utility scale level, useful, they like to use the word useful, error correcting computers. Quantum, obviously one of them. So how do you kind of position yourselves, against them? Is this going to be a symbiotic relationship?
So as I mentioned earlier, people are trying different things, right? Part of the reason why we have this is because no one knows how to do it, right? It's not obvious. And I'm not going to sit here and say that, this platform won't work or this platform won't work. I mean, I clearly have my opinion, right? But I think a thing to say is, every platform has its advantage and disadvantage. And clearly no one has it all. And each of these platforms are working to solve their respective problem. In the case of superconducting qubits, we have decent performance. We have very fast computation, very fast operation speeds. But this notion of scale, right? Like scaling these cables is a very difficult thing for us to do. So that's the problem we chose to solve, is we believe that the best quantum computer is going to be a superconducting quantum computer. And in order to build one that's useful, we need to solve the scale problem. So this is what we're doing. The other people working on other modalities will, tell you what their problems are, and they're working to solve them, and we'll see what happens.
Would it be a little too simple to say, eventually, of course, this is not the best analogy, but let's say yours is an Apple, right? And maybe they come up with a Dell. Like, is that comparison a fair comparison, or would you say
it's a bit more fundamental than that? This is like saying, we all use transistors, right? So we have a shared baseline, right? And now we're kind of at the level where we don't have a shared transistor, right? We're working on different hardware. Is there a potential for multiple platforms succeeding, where essentially some applications are more suited to one than the other? It's possible. I don't think that's what will happen. I do think that we've all come to the not everyone, but the community as a whole, I think, has accepted that a fault-tolerant, error-corrected quantum computer is pretty much the only path to utility. You got to get error correction to work. One of these platforms is going to do that, and that's the one that I think will eat the lunch.
Interesting. Yeah. So very exciting times indeed. Although it's going to take a lot.
It's going to take time, but it's imagine you were in the 40s and 50s building the first microprocessors, right? It's a privilege to get to work under those conditions, and I certainly wouldn't have it any other way.
And there are some chatters that AI may be able to solve the problems in material science and chemistry, all of that, much sooner than any larger scale quantum computer. So what's your opinion on that?
Yeah, I think this is a little bit of a self-inflicted wound by the quantum community. There is a lot of hype out there, right? And people saying, quantum's going to solve world hunger, or solve climate change, right? We shouldn't be saying those things as a community, right? I think that's pretty irresponsible. And part of the outcome of claims like that is quantum's going to solve A, B, C, D, E, F. Is that you have actual computers that exist today that are starting to solve some of those problems, right? That quantum probably never was really going to have an impact on, given that it's 10 to 15 years away. That being said, I think it is also entirely valid to say, yeah, computers today are going to continue to get better and solve more problems. But we know fundamentally, the mathematics are such that there are certain problems that we know we can't solve with AI, right? Or with classical computing. Either it's going to require some massive data set to essentially find correlations in how something works without understanding the underlying physics, right? Which is essentially what you would have to do. Which is, maybe it happens. They kind of did it with AlphaFold, right? Huge data sets, trying to understand how proteins fold. Some people used to say that a quantum computer could definitely help with that. And there's probably some truth to that, but they had enough data to really improve the fidelity of prediction, even with classical AI. So I think that is totally a true thing, right? It's happening. But quantum will come, right? And it will continue to accelerate what we're able to do with computers. It's just another computer in the end. And it's another tool in the toolbox. You have your CPU, your GPU. Nowadays, you have your TPUs, right, for AI. And you're going to have your QPU. And you're going to have a holistic approach to tackling computational problems. You have a problem, some part of it will run on the GPU, some part of it will run on the QPU, send data back and forth, right? This is how it will look. The notion of a quantum computer being a standalone thing is a bit of a misconception. This is just another computational element to help accelerate problems holistically. And there are certain problems we know that we will not be able to get to without either extremely large data sets, which does not exist for a lot of important problems, right? Or a computer that is fundamentally capable of doing that calculation. One could even imagine a universe where the quantum processor it aids your classical AI, right? So maybe it's not necessarily running the actual training, but there are parts of that computation that get offloaded to get run on the quantum processor and then sent back to the classical, right? In order to help the AI understand what's going on better. That could certainly happen. So yeah, I don't see it as either or, right? Both will happen. We know we're experiencing the AI boom now. You go back 10 years, you wouldn't be making, people wouldn't be thinking like we are right now, right? So we're living it. So we kind of know what it can do, and there's some ideas of what it'll do next. But quantum will come and also continue to accelerate compute as a form of improving humanity's predictive power, right? That's ultimately what a computer ends up being. Can I tell what's going to happen before I actually have to do it in real life? And quantum will play just an important role as AI.
And we're sitting here at MIT Engine, and I think you're almost like the quintessential poster child of what they're trying to solve. And talents like you coming straight from an academic lab who's invented technology, becoming now a founder and a CEO. I'm sure a lot of people want advice on that because they're trying to maybe pursue a similar path. So how has the journey been so far for you, and what, advice, you might have for some of those audiences?
Yeah, I mean, I guess what I would say is be motivated to solve a problem, right? And do what you need to do that, right? So I wanted to build a quantum computer. I think it's worth trying to build one. We had an idea, and the way to make that idea reality was to start a company. Now, as part of that, you have responsibilities, right? You have to go and raise the capital, and you have to actually do what you say you're going to do, right? Follow through and continue to raise more and more and more capital to the tunes of billions of dollars eventually, at least. So this is, it's a means to an end. Like I said, I want to get back to doing physics in 30 years from now, right? And everything else is just kind of what I need
computer for that.
What I need to do to get there. And part of it's also I'm excited to work in this field, right? And this is a privilege to be able to do that. Now, on the flip side of this is I do know there is a lot of excitement about starting your own company, right? And being a founder and whatnot. And it is exciting. But really you need to, at your core, need to be excited about the problem you're solving, right? You won't last if you don't have that. And I think that's what people, and also to convince yourself that a startup is the best way to go about that, right? Is the startup the right mechanism to do that in the environment that we're in right now, particularly with the upbringing of VC firms like the Engine? It has enabled things like, startups like ours to exist, right? I'm not so sure that this could have been the case a decade or two ago, right? It would have been a tough sell. At the end of the day, investors have to make a return, right? And the timelines need to match with that of the technology. So really asking yourself, is this not only a worthwhile problem, but what is the correct avenue to channel my time and energy in? And when we founded the company, we felt that this was the best way to do it.
I've learned several things today, integrated circuit, and I think you're going to, on the path to revolutionizing, the scaling of quantum computers. So that's fascinating. So thank you so much.
Oh yeah, I love doing what I'm doing, right? I love working with the people that I get to work with on this problem that I think will have a huge impact on society. And whether that's what that's going to look like, right, is a guessing game. But to even say that I was part of it, I think is what excites me the most.
Excellent. I mean, I gotta really give it up to the deep tech founders, because this is gonna be a long haul journey, right? Maybe 10, 20 years. So you're really in it for the game. So kudos to you. Yeah. All right. Well, thank you so much.